Okay, so we've spent many lectures talking about groups. Now we're going to shift to rings. So this is another algebraic concept that's very useful. Let's get right to the definition. So a ring is a set R with two operations plus and times such that, so first of all, this set R with the operation plus, it should be a group. It should be an abelian group, is an abelian group. Secondly, multiplication is associative. Thirdly, we need the two operations, the plus and the times, to interact a little bit together. So plus and times are distributive. So what this means is that A times a sum B plus C is just AB plus AC, and that if I have a sum B plus C times A on the right, then again this is BA plus CA, and these two are happening for all A, B, C in R. And finally, this is a bit silly, but we should make sure that the identity for the addition is interacting with the multiplication. So we should have that 0 times B is B times 0 is equal to 0 for all B in R. Note here that, so note that 0 is the identity of the group R comma plus. The plus means that we are using additive notation. So product in R comma plus is written A plus B. That's the product in this additive group. And inverse is written minus A in R comma plus. Okay? So that explains what I mean here by 0 times B equals B times 0 equals 0. Now, another comment. So here I have defined a ring as a set together with two operations, and I told you what these operations should satisfy. It should be a group under addition. That group should be abelian. Under multiplication, we require a lot less. We require multiplication is associative, as for the addition, but we do not require that inverses, that multiplicative inverses exist. We do not require that multiplication is commutative. We do require that addition and multiplication are related in this distributive property, and that 0 times any element is 0. Now, a slightly more abstract way of saying this, instead of saying I have a group with two operations, like we did in the group case, we can say that plus, that this is a function from the Cartesian product R times R to R that takes a pair A comma B to A plus B, that minus, that this is an inversion function from R to R, which takes an element A to minus a, and similarly that times that this is again a function from r times r to r, which takes a pair a comma b to a times b. Okay? So both ways, when you're first learning the subject, maybe this way is just a set with these operations, things you're allowed to do to pairs of elements is simpler, but this way of thinking in terms of functions on Cartesian products is also very useful. Okay, so now let's spell out on the board some of the things that I mentioned. So for example, as I said, we don't assume that AB equals BA for all A, B in R. So it might happen that AB is not equal to BA for some pair of elements A and B in R. But we instead, this is an additional property. So a ring R is commutative if AB equals BA for all AB in R. And so note that just to have fun with you and to make you and me and everyone else work harder to understand what's going on, they've used the word abelian for groups and a different word commutative for rings. But this is not my fault. This was decided long before me. Okay. Another thing is we have not assumed that there is an element which is an identity for the multiplication in R. But let's define what this means, and then we will assume from now on that this always exists. So a unit element for a ring R, or a 1 for R, is an element 1 in R such that A times 1 equals 1 times A equals A. So if R has such an element, say R has a 1, or R has a unit element, and from now on, we'll always assume R has a 1. All right. But note that even assuming that R has a 1, still elements of R may or may not have a multiplicative inverse in R. So there may be many elements R in R such that R has no multiplicative inverse in R. What do I mean by this? I.e., there is no S in R such that Rs equals 1. So certainly the element 0 has no multiplicative inverse because we said 0 times b is always 0, except if we are in the 0 ring, the ring consisting just of 0. But there can be many more, and we will soon see examples of this and study more precisely which elements and the set of elements of R that have a multiplicative inverse. Okay, so let's see finally some examples of rings. So the usual number systems that you are all used to are examples of rings. So Z, Q, R, C are all commutative rings with an element 1 under the usual addition and multiplication, and the 1 is the usual 1. Fp, which is Z modulo Pz, the integers mod p. This is another example of a ring. It's again commutative ring with 1. More generally, we could look at Z mod nz for all n, let's say, integers at least 2. This gives another commutative ring with 1. What are some other things we can do? We can look at one of these. So let R be a ring, then R bracket x, this is equal to polynomials in one variable with coefficients in R. So if I have an element f in R bracket x, that means that f is equal to like an x to the n plus an minus 1 x to the n minus 1 plus lower order terms with these ai in R. And so this x here, this should not be thought of as a variable of a function, but as just a formal variable. This is a formal expression. You can then also try to plug in things for it, but you should be careful about doing that. All right, so this, I've given you a set, but R bracket x is a commutative ring with 1 under usual rules for addition, multiplication of polynomials. Okay? And so this construction gives us a lot of interesting examples. So we get Z bracket x, Q bracket x, and so on. Taking rings that we already know, we can take bracket x. And we can sort of iterate this construction. We can take Q bracket x and then look at polynomials in one variable over that. So similarly, what would that give? That would just be the same thing as polynomials in two variables with coefficients in Q. So similarly, we have R bracket x1 up to xn. This is the ring of polynomials in n variables x1 up to xn. All right. Now, let's see an example of what I said, that in some of these rings, it can very well happen that you have many elements that do not have a multiplicative inverse, even though all of the rings that I've written down have a 1. So, by the way, we should say, I mean, the element 0, right? It will not have a multiplicative inverse in any ring except for the 0 ring in which 0 equals to 1. But example, in R equals Z, the ring of integers, I have A in Z has a multiplicative inverse if and only if, well, what does this mean? We know what the inverse of A is in the bigger ring Q. For A to have an inverse, we need an integer B such that A times B equals 1. We know that the inverse of A in Q is 1 over A. We need 1 over A to be an integer. That will happen exactly if A is either plus or minus 1. Okay? So in particular, 2. This is a perfectly good non-zero element of the ring Z. It has no multiplicative inverse in Z. Okay, so now these are all commutative rings, and the main focus in this course is going to be on commutative rings. I will repeat that in a second, but before we leave non-commutative rings, let's just see a couple of examples of non-commutative rings. So what is some very nice non-commutative rings is let R be a commutative ring with 1, then Mn of R. This is all n by n matrices with entries in R. This is a non-commutative ring when n is at least 2. Okay, so for n equals 1, it is just the ring R again. But once n is bigger than 1, then this is a ring under addition and multiplication of matrices. The 1 of this ring, the 1 of Mn of R is the identity matrix. While the 0 of the identity for the additive structure is the 0 matrix. Okay, and I say here all n by n matrices to specify before we were considering the group of invertible matrices GLN. Here we're considering all matrices regardless of whether they are invertible or not. This is, of course, essential. If I add two invertible matrices, there's no reason for the sum to be invertible, but the sum, of course, will be another n by n matrix. Okay? But if this seems abstract, this gives us also a lot of concrete examples because, in particular, we can do this. Like the polynomial ring construction, this is something that you put in a ring and it gives you a new ring, n by n matrices. So I have n by n matrices over Z, n by n matrices over R, n by n matrices over Fp. I can do this to all of my favorite rings. Okay. And these are very nice rings, so this is the topic of another course, but there is a lot to say about them. Let me leave them for this course. Let me give you now just one more example of a non-commutative ring that ties in with something that we did in the group theory. So this is now a separate example. So let H be the set of all A plus BI plus CJ plus DK such that A, B, C, D are in R. Okay, so if you want, I've now just specified for you a four-dimensional real vector space with basis. So H is a four-dimensional vector space over R with basis one I, J, K. Okay, so in particular, a vector space is also something where we have an addition. We have an additive group for that addition. We have the structure of an additive group. But then we have a little bit more. We have the scalar multiplication. Now, I want to introduce a multiplication to make this a ring. So define multiplication using rules to multiply in the quaternion group. Okay, so Q8, the quaternion group of order 8. So remember, we have this circle with the IJK. And if you go counterclockwise, there is no sign. If you go clockwise, there is no sign. If you go counterclockwise, then a sign is introduced, a minus sign. Now, if I tell you how to multiply I, J, and K, then I just say that to multiply any two of these elements, we just declare that multiplication is required to be associative and distributive. And then we know how to multiply. If I take two of these, when I distribute, I will have products of the form some real number, one of these, and two things in the basis and another real number. I'm just declaring that you can take the real numbers out, multiply them like you usually multiply real numbers, and then to multiply the two elements of the basis, use this. So this shows H is a ring, and it's not commutative. Not commutative because we know from this multiplication rule that Ij is equal to minus Ji, and similarly, if you take any two of these three and multiply them in the two orders, you do not get the same thing, but you get the negative of what you get in the other order. Okay? This ring, this is called the Hamilton quaternions. Why is this ring so famous? It's very famous. The reason is that this ring has the special property that what we just said, for example, does not hold in the ring of integers. This ring has the special property that every alpha in H star, by which I mean H minus 0, has a multiplicative inverse in H. Okay? So at the same time, it's not commutative, but it has this property. So as I will next state on the board, a ring with this property is called a division ring. If, in addition, it is commutative, then it is called a field. Okay, so let me just write down what I just said about division ring and field. So definition a ring R in which every non-zero element has a multiplicative inverse is called a division ring. Okay? Some older books or French books also use the term skew field. And then what is more important for us in this course is that a commutative division ring is called a field. Okay? So let's just recap in terms of the examples that we've seen and the definitions that we have now given. So Z, the ring of integers, this is commutative but not a field. R, Q, C, and Fp, where P is prime, these are fields. Z mod NZ, this is again, let's just put it here. This is again commutative but not a field for n not prime. Okay, and then also the polynomial rings that we have seen. So R bracket X, if I take any commutative ring R and I look at the polynomial ring R bracket X, then this cannot be a field because our formal variable X will not have a multiplicative inverse. Okay, and then we said that H, the Hamilton quaternions, this is a division ring but not a field. The n by n matrices, this is non-commutative and not a division ring. Why? So for example, the matrix 1, 0, 0, 0, this is not equal to 0 and does not have an inverse. Okay, so we see that for our various definitions, we basically have, for any two properties, we have something satisfying one and not satisfying the other property. We also have nice things like R, Q, C, and Fp for P of prime that satisfy all the properties and have the strongest one of everything that I've defined, that they are fields. So they are commutative, and every non-zero element has an inverse. Okay, so I just want to add now one example. Here I give you an example in the ring of n by n matrices of an element that doesn't have a multiplicative inverse. In the commutative case, we saw in the ring of integers, let's see in this Z mod NZ, let's see an example when n is not prime. So let's look at R is Z modulo 6Z. Then 2 and 3 have no multiplicative inverse. in R. What is the reason for that? Let's think for a minute. Why does 2 not have a multiplicative inverse? Well, 2 is not relatively prime to our modulus 6. So if we had an inverse, it would mean that 2 times x would be congruent to 1 modulo 6. But 2 times x is always even. Okay? So it means in particular, if I have something that is 1 modulo 6, in particular, it is 1 modulo 2, and so it's odd. So 2x can never be congruent to 1 modulo 6. So 2 has no inverse, and similarly, because 3 is not relatively prime to 6, 3 has no multiplicative inverse in R.